looking at the review of logs, I'm going to start with the exponential growth equation. Okay, some of you may or may not be familiar with this. The exponential growth equation is basically how things grow exponentially. So we have our starting amount, we have our growth factor is what our multiplier is, and then our growth exponent represents the number of growth cycles or how often we apply the multiplier. Okay, and then that gives us our end amount. Okay, sometimes we see it in this way. It's called the appreciation is equal to the principal times the rate to the power of time or something like that. Okay, so it says here, a colony of butterflies grows with a continuous growth rate of 10% per month. Okay, so continuous growth rate looks like this. So continuous growth rate equation is end equals, now it's slightly different than this, it's still start. Okay, now continuous growth rate is when you continuously compound something. So what ends up happening is we end up with E. Okay, so we're not really I'm not going to show you how to do that, but you end up with this formula, E to the RT, okay, where R represents your continuous growth rate. You know, I'm just going to do that in a different color here. So that's our continuous growth rate. Okay, so this is the R here. So what we do in a problem with continuous growth rate problem is all we want to do is just plug in the R into this formula. So our end amount, okay, so it says here, it says find the time it takes to grow from 100 to 20,000. So we're trying to find out the t, so we're going to end up having to use log. So the way you set it up is this. So we end with 20,000. Okay, we start with 100. It's going to be e to the RT. So R is, in this case, our continuous growth rate, and it's 10% per month. Okay, so that's our continuous growth rate. And what we're solving for then is the number of months it takes to get there. Okay, so this equation then, we have our equation. We just need to solve for t. And essentially, we're just going to use logs to do this. So I'm just going to get rid of that 100 to start with. So we end up with 200 is equal to e to the 0.10 t. I'm going to convert this into a log function. So log of 200 is equal to 0.10 t. Okay, so using the log function, I'm going to do that. Then log base e, and then solving for t, my exact value for t looks like this. Log 200 over 0.10. If you want to work out that decimal value works out to be log 200 divided by 0.1. Okay, so 52.98. Okay, so it's 52 about 53 months, 98 months. Okay, so if this is the first time you've seen the exponential growth, the continuous growth formula, that's fine. But this is how we can apply it. Okay, so the continuous growth rate formula has a continuous growth rate R. There's your time, and it's same as the exponential growth problem where we have a start and end value. Okay, so a bank doubles a person's investment every 5 years. So I'm just going to start with a regular growth equation. Okay, so it's going to double every 5 years. So it looks like this. So I'm going to start with $1, and I'm going to double it to $2, and my growth factor is doubling. Okay, so it doubles every 5 years. Okay, so I'm just going to doubles. So that's why I'm using 2 as my growth factor. Okay, and my exponent for this is doubling times by 2 every 5 years. So I'm going to take my years and divide it by 5. Okay, so every 5 years I'm going to use that exponent or that base once, times by 2 once. So there it is. Okay, so that's what it looks like. And if I want to find the equivalent growth rate for this problem, continuous growth rate, I have to set the same problem up with a continuous growth formula. Okay, so I'm just going to do it in a different color here. So it looks like this. I'm going to start with end with 2, start with 1, and then my growth rate formula is ER times T, which we've established as 5 years. Okay, so this is going to give me the growth rate per year. The only variable to solve for is R, and again, this is an exponent in the exponent. So we need to then put this into log form and solve this. Okay, so I'm going to end up with log base E of 2 is equal to the exponent 5R. So R is log 2 over 5. That's approximately, what's the growth rate here? Log 2 divided by 5 works out to be about 0.1386. So I'm going to round that to 0.139 or 13.9% per year. Okay, so that's a continuous growth rate for this problem. So we can also figure out what the annual rate is here by just kind of saying, well, how much would we have increased in 1 year? So the end amount after 1 year at $1 would then give us the appreciation for the 1 year. So if I were to do 2 to the power 1/5, that gives me 1.1486 or about 14.9%. Is that right? 14.86. I'm going to round that to 9. So then this is 14.9% per year, okay, as an annual rate. So this is only compounding once a year. I need this rate. If I can compound continuously, I need a smaller rate to get the same type of appreciation. And that's why we like continuous growth versus, or compounding continuously versus compounding once a year. Okay, so again, this continuous growth rate formula, whether you know it or not, it's not something you need to memorize or anything like that. If you are given a problem like this, you will be given the formula for it, but just understand generally how it works. Okay. And again, I'm just going to color code this. The continuous growth rate is this R right here. Okay.